Hello, this is Ms. Nichols, and this video is on several of the critical circuit equations, including an equation for resistivity, Ohm's law, and what's called the power equation. So the essential question is, what relationships and equations predict the movement of charges and energy through a circuit? So when an engineer designs a circuit, it's useful to think about what variables are independent and just depend on the way I design the circuit versus variables that are dependent. The independent variables in circuit design are voltage and resistance. Those variables depend on the hardware you put in the circuit. It depends on what batteries you put in the circuit and what resistors you put in the circuit. And changing one of them does not affect the other, right? So if I double the number of batteries in my circuit, it doesn't change the fundamental resistance of the light bulb that's in the circuit, and vice versa. So there's really no relationship between those two variables. On the other hand, current and power are dependent variables. So you don't just set a circuit for a certain amount of current or power. The current and power from a circuit or device depends on the design of the circuit and the independent variables that you put in there. Which means if you change either the voltage with the battery or the resistance, both of these two variables, current and power, are going to change. And in fact, if you just change the orientation of things in your circuit, your current and power are going to change. So those two variables are really sensitive to the setup conditions of the circuit. And incidentally, those are the equations that we're going to be developing, the equation for current and the equation for power, as a function of the independent variables. So as I mentioned, there are two independent variables that engineers can control by the devices that you include, and the first is voltage. So every battery or power supply that you use has a characteristic voltage, and the voltage in a battery is determined by what chemicals are reacting inside of it. In other words, specific chemical reactions can push electrons to a particular density, and that strength depends on the chemicals that are reacting. The vast majority of the batteries that you see in your house are those little round ones, right? Those are called alkaline batteries, and they all have the same chemicals inside of them. And since the voltage in a battery depends on the chemical reaction, that means pretty much all those little round batteries are the same voltage. If you look at them, you'll see written on there 1.5 volts, whether we're talking about the teeny tiny AAAs or the big D batteries. They all have 1.5 voltage. That means that the chemical reaction inside of those batteries provides 1.5 joules of energy for each coulomb of electrons that passes through those batteries. If you're trying to design a circuit that has a higher voltage value, you really have two options then. You can put in more batteries, right? So if I stack batteries together, like I'm sure you've seen in some of your devices, each of those batteries can give each electron an energy boost, which means by the time I've passed through 3 of them, I've gotten 3 times as much energy as I would going through just a single one. The other option is to use a different kind of battery that has a different chemical inside of it. So those little lithium batteries, the button batteries, do not contain the same chemicals as the round ones. That means they have a different intrinsic voltage. The second independent variable that you can control in a circuit is the resistance. Now, all conducting materials that allow electrons to flow easily through them have a resistance to this flow of electrons, which basically means as the electrons move, they interact with that material to some extent. They interact with the atoms and the electrons that are in the material, and those electrons sort of impede them or try to slow them down. The overall resistance that an electron encounters when it's trying to move through a conducting material depends on 3 characteristic properties of that material. The first is the resistivity of the material, and this is similar to our thermal conductivity that we've talked about earlier. It depends on how many electrons are free floating in the material that are likely to block the electrons trying to get through. It depends on the atomic structure, the crystal structure of the material. There's lots of things that go into it. But all materials have a constant called resistivity. So copper will have a value, and iron will have a value. And we use the variable rho, which is the same one we used in fluids for density, to represent resistivity of any material. Resistivity has a linear relationship with resistance, which means materials that have a high resistivity also are large resistors, right? They have bigger resistance value, and the smaller the resistivity, the lower the resistance is. So in general, if you're trying to make a good wire that electrons can flow through easily, you want a low value of resistivity. The second variable that is going to impact the resistance of a particular wire is the length of the material. The longer the material is, the more resistance the electron encounters trying to get through it, because it has to pass through more of that material. And that, again, is kind of similar to thermal physics. The third variable is the surface area. Again, just like thermal physics, where if you have a large fat wire, it's actually easier for the electrons to get through. There's like more pathways for those electrons. There's less crowding if the wire is really fat. Which means that we're going to have the bigger the wire, the bigger the surface area, the smaller the resistance, right? So there's an inverse relationship between the surface area of the wire, a chop cross section of the wire, and the resistance of that wire. So if you combine those three relationships, two linear relationships and one inverse relationship, you end up getting this equation for resistance that is on your equation sheet. R equals rho L over A, showing two linear and one inverse relationship. R is going to be measured in ohms. Rho is measured in something. I don't know what the units are. You feel free to work those out for yourself. L is measured in meters, and area is in meters squared. Couple quick examples, right? If you have a relatively thin, long wire that has a material that's pretty hard to get through, that is overall going to have a large resistance. Compare and contrast to this other wire, which is got sort of less resistivity. There's less like things impeding the flow of electrons. Plus, it's also a shorter wire. Plus, it's also a wider wire. So that's going to be a much smaller overall resistance value. When you take like a random device like a light bulb or a toaster, they will have characteristic resistance values that depend on using this equation for all the wires that are inside of them. So the value of resistance of a light bulb, for example, doesn't typically change because the wires inside it are all set. Okay, so let's say we have a really basic circuit with one battery and one resistor, which is a light bulb. In order to figure out the equation for current, which is dependent on both of those values, I would do a little thought experiment and say, if you wanted to increase or decrease the number of electrons that are passing through the wires in this circuit every second, how would you change the independent variables? How would you change the battery and the bulb so that you would get more current? Hopefully it would make logical, intuitive sense to you that more batteries is going to make more current, right? The more energy each electron has, the more electrons get pushed through this system, and the higher the current is going to be. So what that means is that each electron is having more energy. That's going to create a larger current. In other words, current is going to have a linear relationship with voltage. So when I increase the voltage in my circuit, the current is going to go. So there is a second way that we could impact the current in the circuit other than changing the battery. Instead of changing the battery, what if we change the resistor? What if we change the light bulb and we put in a more complicated resistor that has longer wire, in other words, a higher resistance value? How will that impact the number of electrons that are flowing through the circuit? Well, again, kind of logically, if we have a higher resistance resistor, less electrons are going to be able to pass through that resistor every second, and that means we have an inverse relationship between current and resistance. You may have heard the saying, take the path of least resistance, or more people take the path of least resistance. That's true in these circuits as well. So we get more current flowing if there is a lower resistance. So we know that current has a linear relationship with voltage and current has an inverse relationship with resistance, which means that I is going to be equal to delta V divided by R. This equation is known as Ohm's Law, and it's an incredibly versatile and powerful equation. One of the neat things about this is that Ohm's Law is going to work at any level of a circuit. And by that I mean, if you have a circuit that's complicated, that has multiple resistors, Ohm's Law holds true at the level of a single resistor in that circuit. It'll also hold true for any chunk of resistors in a circuit. So the current through a chunk of resistors is equal to the voltage change in that chunk divided by the resistance of the whole chunk. And it's also true for the entire circuit. So the current in the whole circuit, usually defined as the current that's coming out of the battery pack, is going to be equal to the voltage change in the circuit as a whole divided by the resistance. So really useful equation. Obviously, we're going to be working with it a lot. One little note about this equation and the relationships that it shows. This equation, Ohm's Law, represents what would happen in an ideal resistor, a perfect world. If I made a graph of I versus V for a perfect resistor, otherwise known as an ohmic resistor, because they have a linear relationship with each other, you would expect to see a graph that looks something like this. The bigger the I, the bigger the V. That should pass through the origin because there should be no current if the voltage is 0. If the electrons aren't energized at all, they're not going to move. And it actually should continue into the negative values, because if I flip the direction of the current, flips the direction of the battery, the current is pushed the opposite direction. So that's a IV graph for an ohmic conductor. Take a second really quickly and see if you can figure out what the significance of the slope of that graph is using linearization. So pause the video. This would be a useful exercise. Okay, if you're back, hopefully you actually did write this out and figured out what the slope is. If you linearize this, since we have y on the x-axis, that means the m would have to be equal to 1 over r. So the slope of this graph does tell you the resistance, but not directly. You have to take the reciprocal of this slope to get the r. But in any case, what you see is that since the slope is constant, the value of r is constant for an ohmic conductor as well. It doesn't matter how much voltage or how much current is going through a perfect ideal resistor. It's going to have the same resistance regardless. Now, it turns out in the real world, things are never quite that simple. Lots of devices that we actually encounter are not ideal, aka non-ohmic. And in the AP problems, they should specify very carefully whether we're talking about an ohmic resistor or a non-ohmic resistor. In a non-ohmic resistor, the resistance isn't constant. It changes somehow as a function of current. And there's lots of these different devices that are designed to do specific applications in the electronics world. A filament lamp, which is like your old school light bulb that got hot, the incandescent light bulb, you'll see the IV graph is not linear. It would be linear very close to 0, close to the origin. It approximates a linear graph. But the more voltage you throw through these things, right, that slope flattens out. What that tells you is the slope gets smaller, is the resistance is actually getting bigger, right? Because its slope is equal to 1 over r. So for a regular light bulb, if you try to attach an enormous voltage source, if you put too many batteries on your normal light bulb, the resistance actually goes up in that light bulb and the current starts to taper off. We start not increasing current as much. From a conceptual standpoint, this should kind of make sense, because functionally what happens is that light bulb gets really hot, the wire gets really hot, right? And if you think about the atoms inside that wire, then they start vibrating really hot because that's what temperature is. And the more those molecules are vibrating, the more they are likely to bump into electrons that are passing through that wire, therefore increasing the resistance. So this would be an IV graph for a non-ohmic filament lamp. There are also weird things like diodes. So diodes are kind of cool because they only let electricity go through in one direction, and they have a very low resistance for a low voltage value, and then they have a high resistance quickly, dramatically, as the voltage grows up. And in the opposite direction, if you try to throw voltage, flip your battery around, they basically have infinite resistance, which means the current cannot flow that direction. They kind of act as one-way switches and valves. So you don't need to really know about that device, but I just thought it would be fun to show you that it existed. And then there's devices called thermistors. We use these to detect temperature, etc. They have very complicated IV graphs. You can see it's not even IV, it's I, and then we got a log function on the x-axis. So these are all non-ohmic devices. You don't need to know about them other than the fact that non-ohmic means that we do not have a linear relationship between I and V, and the resistance would be changing. So our last big equation for electrodynamics has to do with calculating electrical power, which is another dependent variable. And as I mentioned, in my opinion, this is actually the most important variable, so it's really important to understand this equation. Remember that power is how much energy is transformed every second. We can look at power from the battery's perspective. How much energy is the battery spitting out every second? Or we can think about it as how much energy the resistors are using every second. Of course, these should be the same by conservation of energy. So the energy coming out of the battery should be the same as the energy being used in the resistors every second as well. And as a reminder, the more power, the more light or sound or toast, etc., is coming out of your resistor every second, which is why it's such an important variable. So if you had a circuit designed and you wanted to increase the amount of power to a light bulb, for example, by adjusting the current by adjusting the other variables, there are two ways that you could do this. Number one is that we could increase the number of electrons that are passing through the light bulb, which is the current. And we know that we have to adjust current by changing voltage and resistance. So, current is kind of a secondary variable. But in terms of conceptually thinking about power, it should make a lot of sense to you that the more electrons are passing through a light bulb, the more energy is going to basically be provided at that light bulb or other resistor. So increasing current is going to increase power, and that makes a linear relationship between current and power. The second way to change the power in a circuit or device is to give each one of those electrons that's moving more energy, because if each electron sort of is carrying with it more energy, then overall there's going to be more energy deposited in the resistors as they pass through. So there is also a linear relationship between voltage and power. So here we go. We got our power equation for circuits, which basically says we've got two linear relationships, one with current and one with voltage. So power is going to be equal to I times V. Just for fun, let's look at the units of these things. Remember that a current is measured in coulombs every second, and a voltage is joules per coulomb. So if I multiply those by each other, I have a coulomb joule per coulomb second, and that cancels out to a joule per second, and that, of course, is watt, or the units of power. Okay, so now you've got your three new equations, handy-dandy equations, and lots of new relationships. So please take a few minutes to revisit the essential question, which is what relationships and equations predict the movement of charges and energy in the circuit, and we will start practicing with those equations in class. Thanks for watching.